Hello everybody and welcome back to another episode of Science with Mr. Emond. Today we are going to be continuing in our unit on enthalpy, but we are going to be looking specifically at using Hess's Law. And so we're going to start off today by looking at standard enthalpies of formation. And the first thing that we're going to kind of do here is just talk about what that is. What is a standard enthalpy of formation? So a standard enthalpy of formation of a compound is the change in enthalpy that occurs when 1 mole of a compound is formed from its elements. And all those substances have to be in their standard states. So we write standard enthalpy of formation as delta HF with a degree sign. The degree sign means in its standard state. So it's a heat of formation change in enthalpy of the heat of formations in their standard states. What is a standard state? Well, a substance is said to be in its standard state when it's in its most stable form. And that's at standard temperature and pressure. So how do we know if something's in its most stable form? Well, for most elements, that's when they're by themselves, right? So the standard state of, for example, carbon would just be carbon. And this is actually graphite, right? Graphite is the most stable form of carbon. There's also this form of carbon which looks identical but has a different molar mass, and this is actually diamond, right? They have the same molecular formulas though, so it's a bit confusing. But carbon as graphite is going to be the most stable form as opposed to diamond. So, most of the time, like aluminum, what's the most stable form? It's just aluminum, right? Carbon maybe was a bad example because it's actually carbon and diamond have the same molecular formula. They're just very different structures, right? So usually when an element's on its own, that's the standard state, right? And then you also have to be careful about the actual state. I mean, is it a solid, liquid, or a gas? And for that, look at your periodic tables and you'll be able to figure it out from your periodic table. Another thing to remember are these guys. So in class, we say the Hofbrinkel elements. And this is from Science 10. We had a picture of Hofbrinkel. This is an F, Hofbrinkel. And these are all diatomic molecules. So when they're in their standard state, they're actually found as pairs, right? And so now hopefully you have a pretty good idea about what standard states are and how to know if they're in their standard states. Let's talk about why that's important. Well, we're going to be using standard states to determine the enthalpy of formation of a compound, okay? So anything that's in its standard state has an enthalpy of formation of 0 kilojoules per mole, meaning it's not going to require any energy to get in that form, right? That's its most stable form. For all the other stuff, you're going to need energy above and beyond the energy required to make a stable compound to form that new compound. So let's consider this following equation here, okay? And we're going to be looking at nitrogen dioxide gas and how it's formed from its stable elements. So here's nitrogen dioxide gas. How would you make it from its elements? Well, we need to get a nitrogen from somewhere. What's the stable form of nitrogen? N2. We also need to get oxygen. We need 2 oxygens from somewhere. And what's the stable form of oxygen? O2. What's left to do is obviously to balance it, right? So we have 2 oxygens on the left, 2 oxygens on the right. It's good. We have 1 nitrogen on the right, and 2 nitrogens on the left, which means to balance this, we don't make this a 2. We're actually going to make this 1/2. And why? It's because when you're doing the heat of formation equations, you're trying to show the formation of 1 mole of your product. And in this case, that product was NO2. So this has to be a 1. And that means you're allowed to have fractions on the left-hand side. That's fine. Don't worry about it, okay? We're just trying to balance it, and we're going to balance using fractions. And now we have the standard enthalpy of formation equation, and I'm telling you that the standard enthalpy of formation is 33.2 kilojoules per mole. Now, where in the world did I get that from? Well, that happens to be from a table of values. And that table of values is going to be shown on your screen in just a second. There. So now we're on Schoology. What we're going to be doing on Schoology is going into our unit on heat. Then we're in HT2 now. We're studying enthalpy. So we're going in this folder, and you'll see right here, enthalpies of formation. And when you open this up, you have this very nasty table. It's got a lot of different compounds. And don't worry, this list will get even longer over the course of the semester as I add things to it. This is what I think you'll need. But what were we just looking at? We were looking at nitrogen dioxide, NO2. So let's find it here, nitrogen dioxide. There's the substance. It's in its gaseous state. There's the molecular formula, and what's its delta H? 33.2. So remember, delta H is in kilojoules per mole. So now we're going to go back to our smart notebook. Okay, and here we are. And you can see it's exactly the same. Nice. So that's how these are found. They make equations and then they calculate the heat of formation for them. Let's talk about some important rules that we need to know when we're working with enthalpy questions. So the first one is that if you reverse a chemical reaction, you must also reverse the sign of delta H. Let's look at an example. Here we have xenon plus 2 moles of fluorine gas that are going to be creating xenon tetrafluoride. Okay, this reaction has a delta H of negative 251 kilojoules per mole, which means it's exothermic. Look at what happened here. The reactants became our products and the product became our reactant, meaning they swapped, right? If you reverse a chemical reaction, you must reverse the sign. So instead of a delta H of negative 251 kilojoules per mole, it's positive 251 kilojoules per mole. Now you're allowed to do this, and there's going to be times when swapping your equation around is going to be really useful, and we'll get into that when we start doing practice problems. The next one you really should know, the next rule you should know, is that the magnitude of delta H is directly proportional to the number of moles of the reactants and products. Okay? So if the coefficients in a balanced equation are multiplied by some factor, then the value of delta H has to also be multiplied by that factor. An example, if we have this same equation with the delta H of negative 251 kilojoules per mole, and we want, instead of 1 mole of xenon, you want to have 2. Well, that means we have to multiply everything by 2. So instead of 2 fluorines, we need 4. And instead of 1 xenon tetrafluoride, we need 2 of them. Okay? So now we multiplied everything by a common coefficient of 2. Well, if you do that, if you multiply the whole reaction by 2, so I'm going to try to, show I multiplied this whole thing by 2 to get this new one. Well, then you also have to multiply your delta H by 2. So negative 251 times 2 gives us this new one, negative 502 kilojoules per mole. So those are the 2 rules that you're going to have to live by in this example. So, Hess's Law. Hess's Law states that the enthalpy change for the conversion of reactants to products is the same whether the conversion occurs in one step or many. Okay, so that's a simple definition. Let's look at an example of this. Okay, let's consider this reaction. So we have sulfur dioxide, and it's mixing with half a mole of oxygen gas to create sulfur trioxide. Now, we don't know the delta H for this. Why don't we know it? Because it's not safe to do this one in a lab. because sulfur dioxide and sulfur trioxide are actually toxic chemicals. So you wouldn't work in them in a lab. Instead, if you wanted to figure out the delta H of this, you would apply Hess's law, which is we can separate it into one or more steps to figure it out. So let's figure it out. All right. Step one of this reaction would be to create our SO3, right? And SO3 is going to be created from its standard state compounds. So what's the standard state of sulfur? Well, it's just sulfur. What's the standard state of oxygen? O2, right? And now you just balance. So we had one sulfur on the right, we just need one sulfur on the left. We had 3 oxygens on the right, so we need 3 oxygens on the left. How do you make this into 3? Well, 1.5, which is 3 over 2, times 2 is 3. So you just balance it to make it have 3 oxygens here. And there is our standard states, and this is our enthalpy of formation equation. And when I look at this on a table, I'm going to find negative 441.0 kilojoules per mole for that one. What else do I need to know? I need to know the enthalpy of formation for SO2. Why? Well, because I know it's not 0. This one, do I need to find it? No, not really. Why? It's 0. O2 is its standard state, so I don't need to know that one. But I do need to know the enthalpy of formation for SO2. What's the standard state of sulfur? Well, again, it's just sulfur. What's the standard state of oxygen? It's oxygen. Balance it, it's already balanced. Nice. What's the enthalpy of formation? There it is. So now we need to apply Hess's law. One thing that you're going to notice, okay, is, hopefully you noticed, where is my SO2 in the original equation? It's on the left. Where is it in my enthalpy of formation equation? Of course, it has to be the product, so it's on the right. Well, what do I have to do if I'm trying to add up all the steps and it's supposed to be on the left? How do I get it there? You swap the equation around, okay? And so SO2 becomes your reactants and sulfur and oxygen become your products. I just swapped it. What's Hess's rule? When you swap it, you do what? You swap the sign. So this negative becomes positive, and that's it. Now SO2's on the left. Do we have to do this for SO3? It was on the right before. It's still on the right, so we don't have to touch that one. Now, Hess's law, again, as a reminder, states that if you want to know the enthalpy of formation for a reaction, you could just add up all the steps. So now that we've broken it down into our steps, we can just add them together. So we're going to take step 1 and we're going to add step 2 to them. And what's going to happen here? I want you to take a look at this. We have sulfur on the left and sulfur on the right. It's gone. SO2 on the left, there's no SO2 on the right, it stays. SO3 on the right, no SO3 on the left, it stays. There's oxygen on both sides though. How many oxygens are here? 1.5 O2s. How many are here? 1 O2. Well, if I cancel out 1 O2 from both sides, what am I going to be left with? If there was 1.5 here before, now there's only going to be 0.5. So only 1/2 of them. 1 O2 got erased from both sides. What is my net equation then? SO2, it stays, plus 1/2 O2, that's what's left on the left-hand side, equals all of this right-hand side got erased, and SO3 remains. And what do I do with my delta H's? I just add them together. That's it. So negative 441 plus positive 296.8, that is negative 144.2. And we're done. All right, that's it for this lesson. If you feel like you need a little bit more of an explanation on Hess's law and how it works before we start doing some calculations, you can go ahead and click this link up here to watch the YouTube video of a different teacher who has a very condensed 3 or 4. Thanks for watching, everybody. You can like, follow, and subscribe to my social medias to get notifications as soon as new content is uploaded. In the top corner here, you will find the playlist that this video is in. Watch the unit from beginning to end, and over here, you will find the next video in this unit. Keep learning, everybody. Take care.